Hey guys, it's Miss Maneely, and in today's lesson we're going to do some examples that require the use of Venn diagrams and two-way tables, which we introduced in our last lesson. Since I'm not going to be here for class today, I figured I'd do a quick video so that we didn't fall behind. So in your warm-up, you had some examples that followed what we did last class, where we looked at different events and outcomes and found the probability of those events using just the basic probability rules. So when we're talking about, in this situation, for example, it says, consider the experiment of tossing a single die, and there are 6 equally likely outcomes. We know that on a die there are 6 sides, and they're equally likely, and we're going to define the events as follows. Remember, an outcome would be just the single 1, 2, 3, 4, 5, or 6. When we combine outcomes, then that becomes an event. But an event could also be a single outcome, just like letter A. Event A means that we observe a 2. If we want to write this using the set notation, I would simply say that A, sorry, my board at home is not as nice as using the smartboard. I would say A equals, and then I would use set notation and say that's equal to a 2. And sorry, these brackets, there we go, don't look very good. Let me try typing it. Event B, then, there we go, would look like a 6, because event B only involves one outcome. Event C means that we're observing an even number, so C would equal, that would be a 2, a 4, or a 6 as our outcomes on the die. And a number less than 5, that's what the event D represents, so I'd say D is equal to anything less than 5. So 1, 2, 3, 4. And since we're less than 5, not including 5, I'm not going to put that in the set. Okay, so that's what we mean in part A when we say write each event using set notation. In part B, now we're looking to find the probability of different events. So to find the probability of event A, I'm going to look at how often a 2 would occur. And I know that that's just going to be equal to 1/6. I already know that the likelihood of tossing a 2 is 1/6. Same with the probability of event B. Event B just involves one of the outcomes, and I know that each of the outcomes on a single die is equally likely to be 1 out of 6. Event C, though, remember, represents an even number. And since I have 3 numbers out of 6 that correspond to those outcomes, I know that my probability is going to be 3 out of 6, which is going to reduce to 1/2. In number 4, we're looking at the probability of D prime. And if you remember, D prime is another way of saying D complement, or the complement of event D, which is basically telling you all of the outcomes that are not in D. So for example, if I wanted to say D complement, I would say that that would be equivalent to the set. So if D includes outcomes 1, 2, 3, and 4, then D prime or D complement would involve the 5 and the 6, since those are the only other outcomes possible. So if I wanted to find the probability of D prime or D complement, it would just be 2 out of 6, which is equivalent to 1/3. The probability of A or B. Now, we did learn a general probability rule for the OR statement, which basically says, let me write this down here, the probability of event A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And A and B would be where the 2 events overlap, or where they have the shared outcomes. Now, if A and B are disjoint, and remember we said disjoint means mutually exclusive, it just basically means they don't overlap, they don't have any events in common, then I know the probability of A and B is just 0. And so then my formula for the probability of A or B is very simple. I just have to add the 2 probabilities. So let's think about the probability of A or B in this case, where we've listed A is observing a 2 and B is observing a 6. In this case, these events are mutually exclusive because you can't roll a 2 and a 6 at the same time. So in this case, I can just add the probability of A plus the probability of B. And in this case, I know that that is going to be 1/6 plus 1/6, which is going to equal 2/6, which is going to end up being 1/3. That down here. There we go. Now, if we look at the next one, we've got the probability of C or D. Now, if we take a look at the outcomes that are listed in event C, we know that's 2, 4, and 6. If you look at the outcomes in event D, we can see that the 2 is also, the 2 and the 4 actually, are also in event D. So here we have to be careful because there is an overlap. These two events are not mutually exclusive. So now I'm going to have to use my more general formula and say that it's going to equal the probability of A plus the probability of B minus the probability of A and B. And so let's think about what that's going to look like. I know the probability of A is 1/6. The probability of B is also, oops, I'm sorry. I have to go back and use C and D. Sorry, I totally messed that up. So the probability of C and D, and this would be a C and D. Sorry, I was still stuck on the last example. All right, so I'm sorry. The probability of C we found to be 1/2. So let me fix that. And the probability of D, so D is up here. We know that there are 4 outcomes in D. There's no overlap, so that would be 4/6, or 2/3. And I know the 1/2, let's change this. Let's say they have a common denominator. We'll say event C would be 3 out of 6. Sorry, I totally messed this up. But if I add those two as is, I end up with 7/6, which I know is impossible. I can't have a probability that's more than 1. And that's because I've got an overlap. Events, or outcomes 2 and 4 appear in both events. So I have to subtract the probability of both. And so the likelihood of both of them occurring at the same time, that would be the overlap, getting a 2 or a 4, which I know is going to happen 2/6 of the time. So if I add all of that together and subtract the overlap, I'm going to have 7/6 minus 2/6, which gives me 5/6. And if I think about the outcomes that would make up the event C or D, I'm looking at landing on an even number or an observation that's less than 5. So an even number or less than 5. So that means that 1 would be an outcome, so that's one of them. 2 is less than 5, so that would be an outcome. 3 is less than 5, so I'd need to include that. 4 is less than 5, so I'd need to include that. But 5 is not less than 5, it's also not even, so I would not be able to include that outcome in my event. And since 6, even though it's not less than 5, since it's even, I would include that. And so you can see that there are going to be 5 total outcomes in this combination of C or D. And that's how we get the probability of 5/6. Okay, in today's lesson, we're going to look at other ways of determining probabilities, but we're going to be using models to describe the different situations. So we're going to be looking at Venn diagrams. We're also going to be looking at two-way tables to help us understand the general addition rule and what is called conditional probabilities. Okay, so the first thing we're going to do is revisit the idea of a Venn diagram. So the intersection of events A and B, and we're going to be using these terms, intersection and union. Intersection of events A and B is going to be where they cross. So think about an intersection as where two things cross, where they overlap. And note the symbol that we use to represent an intersection. We use an upside down U. So an upside down U is the same thing as an intersection, and it means the same thing as when both events A and B occur at the same time. So keep those things in mind. An intersection, it's probably easier if I type this. An intersection corresponds to that upside down symbol. Let me see if I can find it in my I don't know that. Actually, these symbols here, the V and the upside down V, are another way to display the intersection. So sometimes you might see it as a V or an upside down V, which is the same thing as the upside down U, which means intersection, and it corresponds to the and that you might see when we're talking about two events. And the union of two events is going to be either A or B or both. So it's going to include the whole thing. That's what union means. So let me just go ahead and write that down. So if we have a union, that's going to be the same thing as a U, or in the case, some books will actually use a V. Let me find that again. Here we go. So that would be another way to express the union of two events. And the union always corresponds to the word or. So it's important to not only understand the symbols, but to understand how it's going to be worded in a problem, because all of the problems you're going to be seeing are word problems. So it's important that you can distinguish between what is an intersection, what is a union, and then the math that goes behind that. So when we're looking at Venn diagrams, this overlap section is what we call the intersection, where both events A and B are occurring. With a union, it's this whole area, either A or B or both. Well, we need to be careful when we're calculating the probability that we don't add the intersection twice. And that's why we have that general addition rule, because if we add the probability of A and then add it to the probability of B, I've doubled this intersection area. So that's why we have to subtract it away. So again, the U or the V is going to correspond to the union of two events, and that corresponds to the word or. The upside down U or the upside down V is going to correspond to the intersection of two events, which corresponds to the word and. Okay, so let's take a look at this example. What is the relationship between educational achievement and home ownership? A random sample of 500 U.S. adults was selected. Each member of the sample was identified as a high school graduate or not. So that's these events here. We either have event G, meaning that they're a high school graduate, or notice we're using the complement G with the, that's not really an exponent, but G of C, which represents the complement of event G, which means that they did not graduate from high school. We also have whether or not the person is a homeowner. So we're using H to denote that event. H equals homeowner, H complement represents that they're not a homeowner. And the two-way table displays all the information for the 500 people. So basically we have 221 people from the sample that are both high school graduates and homeowners. We have 89 that are high school graduates but who do not own their home. And then we have 119 who did not graduate from high school but still own their home, and 71 who did neither. So if we take a look at the questions, it says to construct a Venn diagram to illustrate the relationship between educational achievement and home ownership. So if I take a look at my G, okay, this would be that they graduated from high school. The overlap would be those that graduated from high school and also own a home. So in that overlap is where I'm going to want to put, sorry, I'm going to get rid of that little mark. Okay, so in that overlap is where I'm going to want to put the information of both, where they graduated from high school and own a home. So that's 221 people. So if I go back in here, I can type in 221 in the middle, because those are the people that have graduated from high school and own their home. If I want to look at the rest of the circle G, so this would be all of the high school graduates that do not own their home. And don't think that the area of the Venn diagram has anything to do with the number of individuals that fall into that category. We don't worry about scaling the circles to match, so that's not part of it. So it doesn't, I don't want you to think that because the circle for G, or this part here, the yellow part, since it's bigger than the overlap, that there should be more people in there. That's not what it means. So all I'm going to do is locate the people who have graduated from high school but who do not own their home. So if we go back into our table, we're looking for high school graduate, yes, but not a homeowner. So that would be these 89 individuals. So I'm going to go ahead and just type in 89 here. And then this purple area is going to be all of the homeowners who are not high school graduates. So if I go back here, I'm going to look up homeowner, yes, high school graduate, no. So that would be 119 individuals. Oops. And then the area on the outside would be those people that did not graduate from high school and do not own a home. And so that would be the 71 people right here. And so that's going to go on the outside. What was it, 79? 71, sorry. Okay, and if you add up all these numbers, you should still get 500 since that was the number in our sample. All right, so let's take a look at the label for each of these in the regions in the Venn diagram and interpret the 4 distinct sections in the Venn diagram. And we're going to use symbols as well and the count. So in the intersection of the 2 circles, this would be basically G and H. This would be where we have both, they are both a homeowner and a graduate. Actually, I think the G and H can probably just go in the other category. And then in symbols, that would be, actually, let me do it with a pen. That would be G. And since it's an intersection, I want to go ahead and use that upside down U and H. Sorry, this is so hard to write. And I know that the count is going to be 221. There we go. All right. Inside circle G, but outside circle H. If I think about that, those are the graduates who do not own a home. And so if I'm going to be using symbols, that would be the intersection of G, because they are graduates, and not homeowners. Because anything outside the H circle is going to correspond to not being a homeowner. So if I'm looking at the G circle overlapping that not H, that would be the graduates who don't own a home. And I know that there are 89 people in that group. If we're looking at inside circle H, but outside circle G, that would be the homeowners who did not graduate from high school. Wish I could spell. And in symbols, now it's going to be my H intersecting with not G. So I could also just keep the G first and say G complement intersecting with H. And I know there are 119 individuals in that part of the circle. And then outside of both circles would be those individuals who are not high school graduates and not homeowners. Okay, and so if I'm looking at the symbols, that's going to be where not G intersects with not H. And there are 71 individuals in that spot. Okay, in the next example, you're told information about an apartment complex and about those who read the New York Times. What I'd like you to do is to first create a two-way table that displays the sample space of the chance process. And so remember, a two-way table, you're going to have a variable on the rows. You're also going to have a variable on your columns. So use the information in the problem to help you set up your two-way table. Then construct a Venn diagram to represent the outcomes of this chance process, and then determine the probability that a person reads at least one of the two papers, and determine the probability that the person doesn't read either paper. I'm going to go ahead and press pause and give you a second to go ahead and complete this example. Okay, so let's go ahead and review this example. Again, in an apartment complex, we know that 40% of residents read USA Today. That means if I'm looking in my two-way table, remember we need to have our rows or columns, it doesn't matter how you identify them. One is going to represent reading USA Today and then not reading USA Today. And notice the symbol that I'm using for the not. Instead of using the hyphen or the apostrophe, I'm using what's called a tilde. And that's another way of illustrating the complement of an event. For New York Times, I'm using that symbol to represent not reading the New York Times. So if I know that 40% of residents read USA Today, I know that this whole column has to add to 40% because some of that 40% could also read the New York Times. The second piece of information we're given is that only 25% read the New York Times. So that I know then that my whole row total here has to add up to 25%. And again, that would include people that read USA Today. I'm also told that 5% of residents read both papers. So that gives me the missing information that I need to complete my table. So if I know that altogether we have 25% of residents reading New York Times and 5% of them read USA Today, that means that the other 20% do not read USA Today. And that way, of all of my people that read New York Times is going to add up to 25. If I look at all of my USA Today residents, I know that the total has to add up to 40%. Well, if I know that 5% read both newspapers, then I can go ahead and put 35% read New York Times and not, or I'm sorry, 5% read both and 35% read just the USA Today and not New York Times. That enables me to complete my table because I know that I have to deal with 100% of residents. So I know that whatever is in this box right here in this cell is going to be the percentage of residents that don't read either paper. Well, I know that 5% read both. If I add to that the 35% that just read USA Today, that's a total of 40%. If I add this 20%, that's going to be 50-60%. So that tells me that the remaining 40% read neither. And this way you can just double check to make sure that all of your percentages add up to 100. So this would be 60%, and this would be 75% over here, and that leaves me with 100% of my residents. So you do want to make sure that all of the cells add up to give you 100%. If you want to now translate this into a Venn diagram, the overlap between the two circles is going to represent where they read both papers, and we know that's going to be 5%. If they read USA Today and not the New York Times, that's going to be 35%, and that's going to correspond to this circle right here. If they read the New York Times but not USA Today, that 20% is going to go right here. And the 40% that read neither is going to be on the outside of both circles. And again, if you add everything up, there's 40, 50, 60, it's going to be 65. There gives us the rest of our 100%. And that explains everything. And then in letter C and D, you're actually finding the probability of two events. So in letter C, it says determine the probability that the person reads at least one of the newspapers. Well, at least one means that they either read the New York Times or USA Today. So there's a couple ways I can do this. I can either use my probabilities from the table, which tells me that I would add the 40% of people that read USA Today plus the 25% that read the New York Times and subtract away that 5% overlap. That's using our addition formula. So I can look at this two different ways. It's either going to be the probability of N plus the probability of U minus the probability of N and U, which is simple enough to do mathematically. That's going to be the percentages in my problem, right? 40 plus 25. And I'm going to put this in decimals now. And then I have to subtract the 5% overlap. And that's going to give me 40, 65, 60%. If I want to just use the Venn diagram, I can do it. No problem. I'm just going to add up all of the probabilities that represent the union of these two events, which is just going to be adding 20% plus 5% plus 35. And I should get the same answer. So 20% plus 5, that gives me 25%. 30, that's going to give me 60%. So using the graph, using the Venn diagram, you don't have to worry about doubling up on the overlap because you can just add the 20 plus the 5 plus the 35. But if you're going from the problem or from the information given to you in the problem, it's better to use your rule. But either way you do it, you're going to get 60% as your answer. In letter D, we're looking at the probability that the person doesn't read either paper. Well, that's just the complement of reading at least one. So we can express it two ways. We can express it as not the event N or U, or we can separate it as not N and not U. That would mean that they don't read the New York Times and they don't read USA Today. Either way we look at it, I can just look at my Venn diagram very quickly, and I know that that's going to be 40%. Since they're complements of these two events are complements of each other, I know that it also has to correspond to 1 minus 0.6. Okay, let's go back to our... All right. Oh, and there's a quick exam tip that I did want to point out. It's really important on the AP exam. Many probability problems involve simple computations that you can do on your calculator, and it may be tempting just to write down the answer. But understand that without the explanation, without the communication part, that's the symbols here, or without some sort of written explanation, even the Venn diagram would be better than nothing. You're not going to get full credit on a free response question if you don't explain how you determined your answer. So on the multiple choice, it doesn't matter, but any of the free response questions, you're going to want to make sure that you either use the notation and show your work, or draw a Venn diagram or a two-way table, or what we'll see later on is a tree diagram. Okay, the next type of probability that we want to talk about is conditional probability. And we actually saw this as part of our summer assignment. Remember when we were looking at marginal distributions and conditional distributions? We deal with conditional probability when we have two different variables or two different events, and we're trying to find the likelihood of one event occurring if we have knowledge about the other event occurring. So conditional probability is the probability we assign to an event, and it can change if we know that another event has already occurred. This idea is very key to a lot of applications that we're going to do. So when we're trying to find the probability that one event will happen under the condition that some other event is already known to have occurred, then we're trying to find a conditional probability. For some events, the probability will change, and for other events, it won't. For example, if I know that I toss a coin 6 times and it lands on heads every time, the probability of landing on heads again is still 50%. But if I'm drawing cards from a deck and I've drawn 4 jacks out of the deck, the likelihood of me drawing another jack changes because I know there aren't any more jacks in the deck. So it also relates to our understanding of independence, which is something we've talked a little bit about, but we haven't gotten into much detail. So the notation that we use, suppose we know that an event A has already happened, then the probability that event B happens, given that A has happened, is denoted like this. And notice that it's not a division symbol, it is just a straight up and down line. And this represents the probability of B given A, or under the condition that A has already occurred. For independent events, having knowledge of A isn't going to change anything. It's just going to be the probability of B. But for events that aren't independent, we need another formula. So let's go back to that example that we saw last class with the gender of students in a college statistics class and whether or not they have their ears pierced. So if a randomly chosen student has pierced ears, what is the probability that the student is male? And like I said, we looked at some of these conditional distributions earlier in the year for our summer assignment. But if I think about it, I'm not looking at the whole group anymore. If I'm choosing a student at random and they have pierced ears, I'm now looking just at this group of individuals. Oops. I'm not looking at all 178. So now if I want to know what the probability of that student being male is, it's now going to be 19 out of 103. And the way I would denote this event would be the probability, and if I want to just use M for male and Y for yes, I'm basically trying to find the probability that the student is male. So you're always going to write the probability of the event that comes first. And then the given information is going to go after the segment. So it's going to be the probability of M given yes. And that's going to be 19 out of 103. If I know that a randomly selected student is male, let's change the color here. If I know that a randomly selected student is male, now I'm looking at this group of individuals. And if I want to know the probability that the student has pierced ears, it's going to look a little bit different when I write it down. So the notation now, instead of being the probability of M given Y, is going to be the probability that the person has pierced ears, given that they're male. And so again, I'm only looking at the male students, and I know there's 90 of them. And since I'm only looking at that 90, the probability of the male having pierced ears is going to be 19 out of 90, which is a very different number than before. The formula for finding the conditional probability is, and notice the symbols we're using, the probability of A given B is equivalent to, and this is the same thing as saying the probability, I'm going to have to write this, it's the same as, oops, this is the same as saying the probability of A, and remember that upside down U, it's not union, it means intersection. So it's the probability of both occurring given that event B has occurred. So it's the probability of both divided by the probability of B. Here's another example, and we're going back to the example with the residents in the apartment complex. We're going to say that event A represents reading USA Today, and event B represents reading the New York Times. And the completed Venn diagram is below, and notice that we've even used the symbols, so the overlap would be A and B, and that means that they read both. So what's the probability that a randomly selected resident who reads USA Today also reads the New York Times? So this part here where we're talking about who reads USA Today, that's given information. So that's our given. What we're trying to find is the probability that they also read the New York Times. So if I'm going to write this using my notation, I'm trying to find the probability of reading the New York Times, which is what we called event B, given that they read USA Today, which is event A. And so using my formula, that's going to be the probability of A, or I can say B and A if you want to keep it in order. And I need to divide that by the probability of event A. And so the probability of both B and A is going to be the 0.05, that's where they overlap, divided by just the probability of A. Now you have to be careful because the probability of A includes everything in this circle, not just the 35%. Remember, 40% of residents read USA Today, so I've got to divide by 0.40. And if we do the division, we get a probability of 12.5%, or 0.125. Okay, so there are several other examples that follow, and what I'd like you guys to do is to work together on these practice problems. So in number 5, you're making another two-way table, constructing a Venn diagram just like we did with the newspaper problem, and then you're going to be finding some conditional probabilities along with other probabilities as well. So please use your rules, use the Venn diagram, use the two-way table to answer each question, and what I'd like you to do is at, I guess, about 9:05. I'm going to have you pause the video, and at 9:05, what I'd like you to do is just play the rest so that you can see the answers to these practice examples, and then there's an exit ticket that I want you to do before you leave, and that will help me know what I need to go back over next class in case there was anything that might have confused you. So go ahead and press pause and complete the rest of the practice examples. Okay, let's go ahead over the answers to problems 5 and 6. So number 5 says, according to the National Center of Health Statistics, in December 2012, 60% of households had a traditional landline telephone, and 89% of households had cell phones, and 51% had both. So if I'm filling out the two-way table, I want to make sure that I indicate my landline event and my no landline event, and my cell phone and no cell phone families. If I know that 60% of households had a traditional landline, then I know this column has to add up to 60. I know that if 89% of families had a cell phone, then this row has to add up to 89. I'm also given that 51% had both, and so I'm just going to find the differences to get the landline without a cell phone and the cell phone without a landline. And then since I know all the probabilities have to add up to 1, it enables me to find this missing value of 2% that have neither. When I'm constructing my Venn diagram, I'm just going to plug in these numbers. So I know that 51% have both. That's going to correspond to my overlap. I know that 9% have just a landline and no cell phone. I know that 38% have a cell phone and no landline, and I know 2% have neither. When we start to go through our probability rules, now we have two options. We can actually use our rules. This is the addition rule here. Okay, so if I'm trying to find the probability of having a landline or a cell phone, if I use my general addition rule, that means that I have to add the probability of having a landline, which remember we're given is 60%. And if I add that to the probability of having a cell phone, here, let's look at it from the Venn diagram perspective. I'm adding the probability of having a landline, which is 60% if I add those two numbers together, plus the probability of having a cell phone, which we said was 89%, but we have to be careful because we've added the 51 twice, so I have to subtract it out. That means 98% of families have either a landline or cell phone. That's using the addition rule. If I want to use my Venn diagram, then I've already dealt with the addition rule. That's how I got this 51% in the middle anyway. But if I'm using just the Venn diagram, I'm going to consider where the union is, which is all of event L, all of event C, and that's going to include where they overlap, but I only want to include it once. So if I add these three probabilities together, I'll also get 98%. Finding the probability that a household has a cell phone only, it's really obvious if I look in my Venn diagram, that's just going to be that 38% where we have a cell phone, but we're not in the circle of landline. And it's easy to see also in my two-way table, if I'm looking for just a cell phone but no landline, that means that I'm looking at, again, that 51%, I'm sorry, the 38% that have a cell phone and no landline. Okay, in the next problem, you have to be really careful because now we've got three events. We've got kids that play three different sports, basketball, soccer, and hockey. When you're completing a Venn diagram, you always want to start in the middle with the overlap. And so I know, I'm going to have to work backwards, I know that 12% play all three sports. If I look at my soccer and hockey group, that's going to be this part of my Venn diagram. It's going to include both of those sections. And I know that there are a total of 28%. Well, I've already got the 12% that play all three sports, so that leaves me with 16% that play soccer and hockey but not basketball. If I go up at the next one, we know hockey and basketball, there's 30% that play hockey and basketball. So that means that this whole region has to add up to 30%. Again, I have the 12% that play all three sports. That leaves me with 80%. So your completed Venn diagram should look something like this. To answer the questions, in letter B, it says to determine the percentage of students that play soccer or basketball. Well, I can use my general addition rule, going back to the original probabilities that I'm given. I would just add the probability of soccer, which is 50%, to the probability of playing basketball, which is 66%, but then I have to subtract away the probability of both, which is 22%, because otherwise I'd be counting it twice. And that leaves me with 94% of the students. If I look at just the Venn diagram, I'm looking at playing soccer or basketball. So that means it's this whole circle of soccer players and this whole circle of basketball players, but I don't want to add these two or these three probabilities twice. So I'm just adding up all of the numbers in that union. Because remember, the union is where it includes everything in both events. If I want to determine the probability that someone plays at least one sport, at least one, that's an or statement. It means that they could play soccer or basketball or hockey. It's also the complement of not playing any sports, so 1 minus the probability of no sports. Well, if you've completed your Venn diagram, it makes it really easy. I'm just going to be doing 1 minus 0.04 because 4% don't play any sports. So it makes it really easy to identify the 96% that play at least one sport. If you do want to use the Venn diagram, then I'm basically going to be adding together all of the probabilities that comprise that union, which would be the whole circle for basketball, the circle for soccer, and what's left for hockey. But you just want to make sure that you don't count anything twice. And either way you'd look at it, you're going to have 96% of students play at least one sport. The probability that the student plays no sport, well, we already answered that in part C. Again, it's the complement of playing at least one. And that's an important thing to remember because we're going to see a lot of situations where we're asked to find the probability of at least one. Just remember that that's the complement of none. And that's going to be a really, really important relationship for us to keep in mind, because especially if we're looking at multiple events. So like, let's say I'm looking at a string of Christmas lights and there's 100 lights on them, and I know the probability of any one light going bad, let's say, is 5%, and I want to know the probability that at least one will go bad, then I have to think about all 100 lights on my strand of lights. And so trying to find the probability of at least one can be really challenging. It's a lot easier to look at it from the perspective of the complement, which is 1 minus none. And so that's going to be an important relationship for us to keep in mind. Okay, at this time, I would like you to go ahead and do the exit ticket. I am going to be checking it for accuracy, but I won't put it in the grade book. I just want to see what you understand and what I still need to review next class. Your homework is the worksheet, so please make sure that you get that done as well.